Hello again. This is Math 2-115 coming to you from the College DuPage. And the title of this lecture is Midterm Solutions and Midterm Marking Musings. As always, please be an active learner as you watch this video. Problem number 1, I ask you to consider the following hardware logic circuit and determine the output. And so the inputs were leads that were P, Q, and R. And you had various logic gates, but this is what the output was as a logic expression. And so that's what you had to calculate. And that is P or not R and then this was not P or, and this was Q or not R. And those parentheses, of course, matter. And so these were the inputs I assigned you. Take 1 to be true and a 0 to be false. You had to build a truth table, and your final truth column should be 1, 1, 0, 1, 0, 1, 0, 1. And that's what I got, and that's what you would do on this problem. In problem number 2, I ask you to find a big O estimate for this summation, the summation from J running from 1 to n of J times J plus 1. And your answer was to be a big O estimate. Okay, well, when I'm doing this sum, I can do the algebra inside and I can distribute here, making this J squared plus J. That's what I did. Then I break up the sum this way using the commutative property. And so this is going to be the summation J equal 1 to n of J squared plus the summation J equal 1 to n of J. Now we proved with induction earlier that the summation of the squares is this expression here, and the summation of J from 1 to n is this expression. So this expression manifests as a big O of n cubed, and this expression manifests as big O of n squared. So when you add the two, you should have gotten big O of n cubed. There's a number of different ways you could do that, but this is the way I chose to do that problem. Problem 3. In a version of the computer language BASIC, the name of a variable is a string of 1 or 2 alphanumeric characters, and the upper and lower cases are not distinguished. An alphanumeric character is either one of the 26 English letters or one of the 10 digits. These are 0 through 9. Moreover, a variable name must begin with a letter and must be different from the 5 strings of 2 characters that are reserved for programming use. How many different variable names are there in this version of BASIC? Well, you can be 1 character, but you have to begin with an alpha, so there's 26 1-character variables. If you're 2 characters, what you can have is you have to begin with a alphabet, so that is 26. But your second could be the alphabet, which is 26, or any of the 10 digits, so that's 36. So this is 26 times 36 for 936, and then I have to subtract off the 5 reserved words. So I subtract that off, I get 931. I add that to the 26, and so the total number of variable names are 957 in this version of BASIC. Problem number 4, what is the least number of area codes needed to guarantee that 25 million phones in a state can be assigned 10 distinct 10-digit telephone numbers? This is actually a very real problem. I worked for a company that actually administered the North American number plan. Assume that telephone codes are of the form NXX, that's actually what we call it, NXX and XXXX. Now X can represent any digits, but N, whenever it appears, are digits 2 through 9 inclusive. So this is the area code that's called the NNX, or NNX rather, NXX rather, and this is XXX. Okay, so we have that. So let's then go the problem and see how many area codes we really need. We have 25 million phones, so there is 25 million, and 2 through 9, and I'm just talking about this part of it, but I can have 8, times 10 times 10 times 10 times 10 times 10 times 10 digits. So if I multiply all that together, I get 8 million. So if I take 8 million times 3, I get 24 million. And so 3 area codes isn't enough, but 4 area codes is enough. So the answer is at least 4 area codes. Here's problem 5. This might have been the most difficult problem. This is called McCarthy's 91 function. Anyway, consider, this is a recursive definition, capital M of n is equal to n minus 10 if n is bigger than 100. And if it's less than or equal to 100, it is m operating on m of n plus 11 for all positive integers n. I asked you to compute what is m of 101 and what is m of 76. Now, the reason this is called the 91 function is it turns out that m of 101, well, that's bigger than 100. So I just subtract 10, I get 91. So m of 101 is 91. But what is m of 76? Well, m of 76 is equal to, I have 76 here, I use the bottom definition, and I get this. This is m of 87. But m of 87, by definition again, is m of 98. So I have this composition of recursion functions. But m of 98, m of 98 is m of 109. So I have that. Now m of 109 I can calculate because 109 is bigger than 100, so that is 10. So that this m of 109, or excuse me, the m of 109 becomes 99. So this becomes the 99, and then there are my 3 m's. Now, let's see, let's continue. So if I have m of 99 going from here to here, that is m of 88. And m of 88 going the other way is m of 99. You want to work through this and think about this. Now you might say, wait, we're back where we started. No, you're not. Here you have 3 m's, here you have only 2. So m of 99 then, using the definition going this way, is m of 110. But now 110 is bigger than that, so that is going to be mm of this is m of 100. And so what happened is then m of 100 is m, and then that is m of 111. And this then is the same thing as this part right here is m of 111 is 101, and so that ends up being m of 101, and that's equal to, when you subtract, that's more than this, you subtract, you get 91. And so m of 101 was 91, and m of 76 is also 91, and so z is 91 and 91, or 182. You get m of n for being less than or equal to 101. You get 91. Above it, just grows by 1 each time. So that's what we get. And for this one. Number 6 was a relational database problem. You have a parts needs database and a parts inventory database with these things. And I ask you to find a complete answer to this query. And the query is, I want you to select supplier and projects from this database and this database where the quantity is less than or equal to 10. So your answer was to be a set of ordered pairs supplier and project where the quantity is less than or equal to 10. Well, when you look at the parts inventory database, you see that there are 4 parts that are less than or equal to 10 in inventory. But then when you look at the other databases and you look at those parts, you see that they're aligned with supplier 23 and projects 1 and 3, and also supplier 31.3 and 32.4. So this is the answer to the problem. So this is the answer to the query that you should have. So this is the answer I was looking for. Problem number 7, another counting problem. A group of 15 candidates for 7 identical positions consists of 6 women and 9 men. So these are the people who are vying for the positions, and you're randomly selecting them. You're not really interviewing them, you're just grabbing a hold of people. Are selected to fill the positions in such a way that there are more women hired than men. How many different possible sets of hired individuals is possible? So you see the order doesn't matter, it just matters if you're hired or not hired. So if you're thinking about that, if there are going to be more women than men, what you can do is you have 15 candidates, 6 women and 9 men, but there were 7 positions, so the most number of women you can have is 6, 5, and 4. But these will be cases where, and they're disjoint cases, but these will be cases where there are more women than men in the hiring slate. So we'll look at these each in turn. So if there's 6 women, it's 6 choose 6, but then I have to choose a man. So there's 9 choose 1. If there are 5, there are 6 choose 5 women times 9 choose 2 men. And if you choose 4 women, it's 6 choose 4. And this is 9 choose 3 is the men. You multiply those together. This is kind of the formulas from Excel. And here's what I get when I do it. And I add up these things because those are disjoint subsets. So it's going to be 1485 is the answer you should have come up with. It's amazing how these numbers get so big. Problem 8 was about set theory. We let AI, A sub I, be the set of all non-empty bit strings. So it does have something in it. That is bit strings of length at least 1, and these are zeros and ones, of length not exceeding I. So A1 can only have 1 digit. So it could be a 0 or it could be a 1. A2 can have 2 digits. So it can be 0, 1, 2, or 3. Represented that way. And A3 can be 3, so it is 0, 1, 2, 3, 4, 5, 6, and 7. Those are represented in binary. So, and if you're taking the union, you get all of those. Those things do overlap, but I don't have to list them more than once. So this is the answer that you want to have for full credit. Now that was the union. This is the intersection. So you see these things are nested. These are 2-bit sequences. These are 3-bit sequences, and there's a 1-bit sequence, but they only overlap in terms of the not exceeding I. So that means, you know, these things intersect just with a single bit sequence. So this is just 0 or 1. And those are the answers that you should have had for that problem. Number 9, consider the following proof for the proposition. Is it valid? If invalid, explain why. So we wanted to prove for all n plus 1 is less than n. Well, we assume that n is equal to k, and so that's our assumption. And we do k plus 1, and we do the calculation, and we then can say, oh, so this holds for k plus 1 when we assume it held for k. So we satisfied the induction hypothesis. Therefore, by mathematical induction, it holds for all positive numbers n. Well, this is invalid. In fact, n plus 1 is bigger than n, not less than n, for all n. The induction proof fails because we did not have a base case. Normally you say, oh, is it true for 1 or 2 or 3? Some domino gets knocked over first. The first domino is never knocked over here when I use the domino analogy. So you want to say something to that effect, but this was an invalid proof. Here I ask you to prove or disprove that the smallest integer greater than or equal to x of x plus y is equal to the smallest integer greater than or equal, these are called ceiling functions actually. So the ceiling function of x plus y is equal to the ceiling function of x plus ceiling function of y for all real numbers x and y. And I reminded you of the definition that the ceiling function is the smallest integer that is greater than or equal to x. Well, it turns out this is not true. You just can give a counterexample. And the counterexample, I can say x equal y equal 1/2. So if I take 1/2 plus 1/2 inside, I get 1, and the ceiling function of 1 is 1. But if I take 1/2 separately, the ceiling function of 1/2 is 1. The ceiling function of 1/2 again is 1, so that is 2. 1 does not equal 2, so this is not true because I gave a counterexample. Here I ask you to do an algorithm, and so what you do is you input AB, you checked if B was equal to 0. If B was equal to 0, you just printed A out. If B was not equal to 0, and you ask the question, is A bigger than B? If so, you replace A by A minus B. If B is bigger than or equal to A, you replace B with B minus A. And then you just cycle through doing that, and eventually you print A. And I ask you to start with A equal 91 and B equal 63 and find the answer to the algorithm. So you had to go through the steps. We went through, I don't know if that's 7 or 8 steps. I guess that's 8 steps. And you get that A is 7 at the end of the problem, because when B is equal to 0, you just print what A is, and A was 7 in the previous step. This is called the Euclidean algorithm for finding the greatest common divisor. Number 12, the last problem. Demonstrate whether the function that was introduced in problem 5, this was the McCarthy 91 function, is 1-to-1. And, well, it's not 1-to-1 because m of 101 is the same as m of 76. In fact, the answer is often 91. And both of these are 91, but 101 does not equal 76. So this is not 1-to-1, and that's a proof by counterexample. Now, I am going to be grading this probably starting tomorrow morning. But this is going to be my rubric. Again, as I told you, the answer sheet is the primary grading instrument. If I find the correct answer on the answer sheet, you'll get full credit. This was a proctored exam. If you have an authentic answer but wrong, you can't go through and just put pi for every problem, because the answer, in fact, to none of these problems was pi. But if you have an authentic but wrong answer, I'll give you half credit. It does on a problem. Now, it does matter getting the right answer, so that's why I'm grading it that way. The PDF you submitted as a secondary instrument, and I can look at that. But there were 12 problems. I'll convert whatever happens with that to a percentage out of 100%, and that's going to be your score, and I'll be posting that sometime in the pretty near future. Now, I do have to, or I do want to, I don't have to, I guess, but I do want to give you some indication of midterm standings and things like that. Anybody who engaged well on the exam should have scored at least 50, because, if you got credible answers for all the problems, you could have got a 50. Now, I am being very generous because I want to be on a wholesome discipline. Grade gently, especially during COVID times. So your low stakes assessments year to date, I generously gave you 100 for that. So everybody has 100 there. These are midterm scores. These are hypothetical students, but I kind of spanned what I expect to be the grades that I find students earning from 50 maybe to 100. And then what I will do is this is going to be 1/3 of your final grade. Actually, this is just year to date, and we're going to have other low stakes assessment. So this is not the end of a low stakes assessment, but it is year to date. I was generous during the first half. I might not be quite as generous the second half. We'll see. But anyway, this was good. So year to date, I gave everybody full credit. Some of you deserved that. Some of you less so, but I was generous both ways. Your midterm counts the same as the low stakes assessments count, so I took the average of these two to come up with a percentage, and so these three scores would have you sitting at an A. At midterm, this two would have you sitting at a B, and this would have you sitting at a C. Now, this is a real genuine, I think, perspective of how I probably will approach grading. So the tests do matter, but I also was generous up here, and I think people should be in fine shape. But this is the real perspective. Now I do have to file with the college grades, and I think they're actually due probably tomorrow, maybe even before I finish grading these. So I'm going to turn in S for satisfactory. Everybody gets a satisfactory, or U for unsatisfactory, and that's all they want is a S or a U. So that's what you're getting. But this is the real perspective I think you should think about. Now, the final exam does count. It is comprehensive, and it counts at least as 1/3. So it'd be 1/3, 1/3, 1/3. You remember that. But since the final exam is comprehensive, and I believe in students having every opportunity to do well, so since it's comprehensive, that means it covers everything in the course, what we did earlier and what we do going forward. So since it's comprehensive, I will award a letter grade no lower than that earned on the comprehensive final exam. That means you could have scored poorly on the midterm, but if you get an A on the comprehensive final exam, you can earn an A in the course. Please regard this as being a significant opportunity and stay engaged during the rest of the course and learn from these solutions so that if I ask similar problems on the final, you can do even better. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.